Okay, and today I think about the first version of our ARM and the initial users of our ARM and the demo that we need to make for them. So I decided to think through all the options. So when we have this discussion about our initial plans, we have already sought out options. Because there was a lot of questions about initial users and who are them and where can we get it. Yeah, and also today I helped Victor to set up this configuration, which is quite annoying, but finally we make it work. And during the weekend I watched a cool video about TDMPC paper about RL in real life. That's my check-in.
We assembled one set of arms. Now we have both of them, leader and follower. And stop configuration for it. We used script to write parameter to each motor. It not work at first, and we need to do several iterations with scripts to finally make it work. And took this configuration screen with all correct indexes, write it into firmware of the motor.
Today I tried some test training of diffusion policy model. We still don't have a lot of data, so the model right now is still really bad. But one interesting thing is we can see the evaluation. In the evaluation, we can see every time we open the evaluation, the inference policy are different. The robotic arm can choose different paths to do the execution. So this is obvious difference from ACT model. We think this feature can help us in the future to make the model to be more robust to different environment. But on the other hand, we also see the inference speed is very slow. We need to further debugging to see where is the bottleneck of the inference.
Today, I read some papers about robot arms, what do people do with it. Because I'm not a robot expert, I worked on computer vision before, so I'm kind of new to this field. So I wanted to know what kind of things out there and what's the main limitation, and more importantly, how we can make an improvement over ACT model that we trained on the simulation. So I'm going to introduce several papers, but then I didn't read all the papers I'm going to talk about. I just kind of tried to categorize them and then get the high-level idea. Okay, so let's first take a look at ACT model. So this is the paper, and this table shows success rate of the ACT model on different tasks. I'm interested in real-world tasks, so this is simulation, and this is real. And then for a certain task, it achieved like 88% success rate. For the slow battery, it's 96. It's better than the Ziploc. But then on the cup, it's like 84. The Velcro is like 20. Tape is like 64, something like this. So the first thing I can see from this is that the accuracy or the success rate is not high enough. It's far from production, right? In many production cases, we have low fault tolerance. So people often say we need like 99.99% success rate. And then so far in the computer vision world, I think how people made it work is coming up a good model architecture, nice loss function, good regularization. But then in the end, I think most important thing is data. So people collected a lot of data. It's same for the language, right? LLM. And then train a bigger model that can consume that big amount of data. And then we'll have a really good accuracy, right? So I thought that's the first reaction for me when I see these kind of accuracies or success rates. But then this ACT model in particular has somewhat different story. So this is imitation learning, so it learns something from expert demonstration. So it's difficult to collect like millions or billions of expert demonstration for a certain task. That's not scalable. And the second thing is that the success rate kind of plateaus after you collect like 100 or 200 expert demonstrations. So like this data is not helping ACT model, right? So that's like so it means we need a kind of different approach. And the second thing I see from ACT is that this one is trained per task at the particular environment. So if the environment changes, like the camera angle changes or lighting changes or some height changes, or robot changes, right? Then it's gonna be very difficult to be generalized into those scenarios. Then when you think about the production, I think there will be a lot of like a diverse real world cases that you need to cover. So that's the second limitation. So in terms of like a data part, people start to accumulate a lot of data on the robotics within like 1 year, I think. So this one is one example, OpenX embodiment from all these like institutions that collect the data all together. Let's see how many like 22 robots, 500 skills, 60 data sets, and then it has like 1 million real robot trajectories. It's not to the level where LLM is trained like billions. Like a million is small scale data, right? But then for robot, I think it's difficult to take or scale to the level of image or language data. This is another work, bridge data, similar, and some household tasks by manual robot. Yeah, and then people just start to try to leverage this big data set to train somewhat generalist models. Like OpenVLA, you see that almost 1 million robot episodes, and then you train some LLM with the VIT. So it's basically a vision language model, and then you output action. So it's a vision language action model. Something like this, or Octo, or I believe there's more papers working on this. So this one is more like generalist approach. And then there's another line of work is that, okay, ACT is there. Can we make something better than the ACT? So a diffusion policy came out similar time as ACT. I think they are very similar, except that ACT used conditional variation autoencoder and diffusion policy used diffusion to get the policy. But then if you look at the next version of Aloha, so Aloha is a hardware, and then ACT is a software part. And then the authors made a new paper, Aloha Unleashed, and then they're using diffusion policies. So I think it kind of tells us that a diffusion policy is also, good replacement of the ACT. And there's another paper called VQBET. It's a little bit different approach. So these are the approaches that try to make a different architecture or the kind of model changes, right? And then there's another line of work that tries to use reinforcement learning. So given that there's an imitation learning where you learned good enough initialization from expert demonstrations, now you have like 80% success rate. But then can I push the envelope and then and then make it much better, right? Using RL. So these are the works doing that. Fine-tuning offline world models. This is the paper. TD-MPC and TD-MPC2. Modem V2. They all try to learn the imitation learning, make the imitation learning better using RL. So I think that's good approach. PWM is more recent one. I think this is the state of the art based on the experimental result on this direction. So given that there are three directions to make ACT better, one was make it a generalist so that it can be generalized in different scenarios and let's say different cameras and stuff. And second thing was make a better model architecture. And third thing was like push the limit using RL. And among these three, I think generalist has low price because I first want to have a model that works really well and then make it generalizable, right? It makes less sense to me to make the model generalizable first when the model doesn't work, right? So I'm more interested in the second or third approach, and I think the third approach, the RL, is more promising to me. Like I don't know about RL. Maybe that's why I think it's promising. But from the approach perspective, this RL can be applied to any imitation learning methods. So if there's some really good imitation learning method came out, I can still use this RL to push the envelope, right? So I think I wanna learn more about this RL approach and then actually apply it to our simulation or real world data. Yeah, so that's my plan.